Okay, we're going to talk about ionic compounds. There's lots and lots of ionic compounds. They're present in the Earth's crust. They're present in the food we eat. Ionic compounds are generally very stable because the forces of attraction, the ionic bonds that hold those ions together, are very strong. And so it takes a lot to break up an ionic compound. Just some examples here. Morton's light salt is a mixture of sodium chloride, which is the regular table salt, and potassium chloride. And by mixing these two, you get a lower sodium content. So if you're watching your blood pressure, you can salt your food and not have quite so much sodium. Calcium carbonate is found in antacids like Tums. So those are things that you might ingest. There's lots more ionic compounds that we ingest. Here are some things you should not ingest. Calcite. This is also calcium carbonate, but that's not going to help you with your heartburn. And trona, this has this big messy looking formula. We can see this is an ionic compound. It starts with a metal. Okay, so there's another ionic compound. So we need to learn how to write formulas for the ionic compounds. And here's a list of steps for those of you that like lists of instructions. You need to write the symbol for the metal cation with its charge. Write the symbol for the nonmetal anion with its charge. You got to have the charges so that we know how to put them together. We're going to put them together in a way that the charges are going to add up to 0. And so if we need more than one of the cation, we're going to use a subscript. So we're going to use subscripts on each of the cation and the anion so that overall the charge adds up to 0. Because ionic compounds overall are electrically neutral. And then you always want to double check that things are working out okay. So things to remember, ionic compounds always have a positive and a negative ion. You can't have two negative ions, they will repel each other. The first element is usually a metal. The notable exception for this class is the first ion, the cation, may be ammonium, NH4 plus. Okay. In the chemical formula, the sums of the positive charges and negative charges have to be equal. Yeah, equal, or add up to 0. And we're looking for the smallest whole number ratio. So sodium chloride we represent as NaCl. If you wrote Na32, Cl32, well, technically, yeah, it's the same ratio, but it looks weird, right? The goal of nomenclature is to have one best name for every compound, one best formula, because otherwise it gets very, very confusing. So we go with the lowest ratio. Let's do some examples. Write the formula for the ionic compound that forms between potassium and sulfur. Potassium's a metal, sulfur's a nonmetal. We expect an ionic compound. We need the charges and on the symbols here. So potassium is K. What charge do potassium ions have? +1. Because they're in group 1A. All the group 1 elements form +1 ions. Sulfur. What charge does a sulfur ion have? -2. So we know that from its position on the periodic table. Now we need to figure out how can we put these together? How many of each do we need so that they're going to add up to 0? K2S. So people's brains work differently. Some of you can look at that and just know that it's K2S. So you don't need me to explain this. A lot of the rest of you are not real sure what to do with this. There's two methods I'd like to show the rest of you. I'm going to do the visual one first. So we know that the total positive charges and total negative charges have to be equal. So let's just see where we are. We've got a total of +1 from the potassium and -2 from the sulfur. Those aren't the same. We can't make them lower, we can't cut things in half or change their charges. All we can do is add more ions. If we add another sulfur ion, we're going to make things worse. If we add another potassium ion, let's draw it in. Add another potassium ion. Now the total over here is +2. +2 and -2. This is good. They would add to 0. Same number, opposite charges. So then for the formula, I look, how many ions do I have? Well, I have 2 of these, so I write K with a 2 after it. And I've got 1 of these, so I've got the sulfur, and I don't write anything because there's just 1 of them. Any questions? There's also the crisscross method. A lot of students like this. There's nothing really wrong with it. It doesn't always work, but it works most of the time. So in the crisscross method, what you do is you take the charges and you crisscross them, and they become the subscripts. So here we have an unwritten 1 as the charge here. That becomes the subscript on the sulfur, an unwritten 1. This 2 becomes the charge over here on the potassium. And then we just copy it down, K2S. Works most of the time. Any questions? Pick the method that works for you. If you can't find a method that works for you, please come and talk to me because I can come up with others for you. Let's do aluminum and nitrogen. Well, what charge does an aluminum atom have? 3+, because it's in group 3. So we've got Al 3+, and what's the charge on a nitrogen ion? 3-, based on its position in the periodic table.
We need to put a 2 in there since the diatomic.
That's a good question. Should we put a 2 in there? Nitrogen is a diatomic element. No, because here it's not by itself.
Okay. So if it's by itself, then
If it's by itself, it's going to be 2. So that reminds me, I think of metals as being masculine and nonmetals as being feminine, and those 7 diatomic elements remind me of junior high girls. I was once a junior high girl, and we had some rally or something, and the speaker pointed out that junior high girls tend to go to the bathroom in groups. You know, you need to go pee. You take a friend with you, right? It's just a thing that junior high girls do. So I see these, like the junior high girls, you're not going to see any of those 7 diatomic elements out by themselves. Now, they're not always with the girlfriend, so it's not always N2. Here, nitrogen isn't alone. Nitrogen's with a boy. Okay? But you're not going to find nitrogen atoms alone. They're insecure. Okay? So good question. What are we going to do with these guys? What do we do with the charges? Nothing. +3, -3, it's fine as it is. We just need 1 of each. So I think of pushing them together, and we've got ALN. If you crisscross these, you would not be quite correct. You'd get Al3N3. And then you'd have to simplify that. So if the charges are the same, just push them together, 1 of each. So that's not technically correct. Any questions? How do we name them? Some compounds have common names, but every compound has a systematic name. And this was done not to annoy chemistry students, but to actually simplify things. If you can push through learning this until it clicks, you'll see that the system is actually as simple as it could be. So we have to identify what kind of compound. So right now we're just talking about ionic compounds. And we identify them because they're usually a metal and a nonmetal. There's a metal, 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 metal. These all have metals in them. The exception would be if it starts with NH4. Of the metals, there are the ones that we can predict their charge from the periodic table, and they always form just an ion with the same charge. And then there's others that are less predictable. So that's what your book calls these 2 different types. So these are the metals that always form the same ion. So the ones in group 1 form +1 ions, the ones in group 2 form +2 ions, and aluminum in group 3 forms a +3 ion. Zinc also is predictable, and so is silver, and you need to know these guys. So aluminum is +3, zinc is +2, Silver is +1. I remember that because I think of coming down the stairs. 3, 2, 1 on a diagonal. These ions have the same name as their element. So Li plus is called lithium ion to distinguish it from a lithium atom. But there's nothing else funny in its name. Then everything else, all the other metals, can form 2 or more different ions. And so then we've got a little bit of a problem. Let's look at iron. So iron can form a +2 or a +3 ion. Well, we can't just call them iron ions because which one are we talking about? So I should think of a famous name, but I can't think of one. So I'll go back to John Smith. So this guy named John Smith named his son John Smith, and the son grew up and had a child and named his son John Smith. How do we keep track of which John Smith we're referring to?
First, second, third.
First, second, third, right? John Smith the first, John Smith the second, John Smith the third, John Smith the fourth. Some families get a little carried away with that. That's a lot like what we're doing here. We're using Roman numerals to distinguish between two things that are very similar. The difference is the charge. The Roman numeral tells us the charge. So Fe2 plus is called iron 2 ion, like iron the second. Fe3 plus is iron 3 ion, like iron the third. We use Roman numerals because we use Roman numerals. There's an older system that I want you to know that it exists so that if you see it, you can go look up what it means, but you don't need to learn these. So they used to call iron 2 iron ferrous ion, and iron 3 was ferric ion. And that is still used in some places, in some situations, but I'm not going to do that to you on an exam, okay? So I have my little tricks. Group 1A, +1 charge. Group 2A, +2 charge. And then this triangle. Aluminum, zinc, and silver are the ones we're going to run into the most. Gallium, cadmium, and indium also form predictable charges, but we're not going to worry too much about them. Gallium and indium are in group 3A. They form +3. Zinc and cadmium are both +2. Silver is +1. So metals in groups 1A, 2A, 3A, zinc, and silver do not use a Roman numeral. All the other metals do. On the previous slide, no, this one, scandium over here. Scandium's always +3, but we almost never run into him, so I just left him off. So groups 1A, 2A, 3A, zinc, and silver, no Roman numeral, just the element name. If it's not one of those, you have to use the Roman numeral. So those are the cations. There are monoatomic anions and polyatomic anions. Monoatomic means it's just one atom that's an ion. So the nonmetals, the charges are predictable from the periodic table. You can either count backward from the noble gases, or you can look at their group number -1, whatever works for you. The names of these, we change the ending of the name to "ide." So I told you I think of nonmetals as being feminine, as being women. So traditionally, a man and a woman get married, and who changes her last name? The woman. So here, the nonmetal is changing the ending, the last part of its name. So fluorine, when it becomes an ion, is fluoride. Chlorine is chloride, etc. A binary ionic compound just has 2 different elements. So we're starting with the simplest ones. To name these, you name the metal, the cation first, and then you give the name of the anion. Why do we do it this way? Because we decided to do it this way. If you address a formal wedding invitation to, your aunt and uncle, you're going to write Mr. and Mrs. Why? Is it because women are oppressed and we're inferior to men? No. It's just because that's the way we do it. It's just consistent, Mr. and Mrs. So it's the metal and the non-metal, same order. So KCl, the cation is potassium. It's in group 1A, doesn't need a Roman numeral. So the name of the cation is potassium. Chlorine becomes chloride, and so the name of the compound is potassium chloride. It is not capitalized. It's not a proper noun. There is a space between the two words. Just like when you write your first name and your last name, you leave a space between the two names. For calcium, for CaO, see, I see this and I just sometimes read it as the name to stop myself. CaO, so we have a calcium ion. You ask yourself, is it in groups 1A, 2A, 3A, zinc, or silver? Yes, it is. It's in group 2. No Roman numeral. Because we don't want to be having to write a whole bunch of extra stuff. We're trying to be efficient, and so we're not writing more than we need to. So calcium ion is just calcium. And then O, oxygen changes the ending of her name and becomes oxide. So we've got calcium oxide. Any questions? Let's name Ag3N. Well, what's the name of this element? Silver. Okay. So the first name of this compound, because it's got a first name and a last name, is silver. Then we ask ourselves, is that in groups 1A, 2A, 3A, zinc, or silver? Yeah, it's silver. It's right. Groups 1A, 2A, 3A, zinc, or silver. No Roman numeral. Cool. Okay, so the other one is nitrogen. How do we change that? Nitride. So this is silver nitride. Okay? If you put a Roman numeral in there, I would know what you mean, but it's technically not correct. Okay, any questions? How would we write the formula given this name? Rubidium sulfide. We need the ions. So what's the symbol for the element rubidium? Rb. What charge does a rubidium ion have? 1+, it's in group 1. Okay, sulfide. What charge does a sulfide ion have? 2-. So whatever method works for you, how do we put those together? Rb2s. That's the formula. Any questions? What if the element, the metal, is not in groups 1A, 2A, 3A, zinc, or silver? Then we need to put the charge of that metal ion in Roman numerals in parentheses right after the name. There's not a space between the name and the Roman numerals. There is a space over here. They didn't show it, but it's supposed to be there. How do we figure that charge out? Well, we have to look at the relative numbers of cations and anions and the charge on the anion and figure it out. So let's name this one CrBr3. There are 2 ions. One is the Cr and one is the Br. We have Cr and we have Br. So we have a first name and a last name. Cr is the symbol for what? Chromium. Is chromium in groups 1A, 2A, 3A, zinc, or silver? No. Does it need a Roman numeral? Yes, it does. I'm going to put the parentheses in there so I don't forget to put the Roman numeral in there, and then I'm going to go on and write the last part. Bromine becomes what? Bromide. Whoops. Okay, so chromium something bromide. How do we figure out the charge? Well, we need the charge on the anion. What's the charge on a bromide ion? 1-, -1. Okay, so sometimes when you're not sure how to figure something out, drawing a picture can help. It's not really much of a picture, but the visual representation of what we've got here. CRBr3, that tells me there are 3 of these ions, and there's 1 of those. So the total charge from these negative ions is -3. That means the total positive charge has to be what? +3. That +3 charge is shared equally among all of that only 1 atom, right? Sometimes you have 2 or 3 and you have to divide it up. It gets divided equally. Here there's only 1 positive ion. It must be 3+. That's how you figure out the charge on the cation. And so it's got a charge of 3+, so I write the Roman numeral 3 in parentheses. Any questions?
If it's negative, do you still just write that?
If this was negative, it will never be negative.
Well, that makes it easy.
That makes it easier, yeah. Because this is a metal, and metals always form positive ions, so it won't be negative. Any other questions? Name this compound. I think we should call him Fester. That'd be good. That's Fester. And then write the form. No, let's actually name him. So Fe is a symbol for what element? Iron. Is iron in groups 1A, 2A, 3A, zinc, or silver? Nope. Needs a Roman numeral. Put a space there. Sulfur. We're using an awful lot of sulfur. What does that become? Sulfide. So we've got most of it. I don't know what's going on. To figure out the charge, we have to look at the charge on the sulfide ion. So we've got 1 iron ion and we've got 1 sulfide ion. Sulfide has a -2 charge. If you're not sure how we're getting these charges, ask me in lab. I've got 1 of each, so that makes it a lot easier. If I've got 1 of each, the charges must be equal. They're just opposite in sign. So this is iron 2. Any questions? Okay, let's write the formula for ruthenium-4 oxide. If you're a little rusty on your Roman numerals, you can Google those. What's the element symbol for ruthenium? Ru. What's the charge on a ruthenium ion? We don't know from the periodic table. We do know from the name. 4. 4+. And oxide is oxygen. What's the charge on an oxygen ion? 2-. The numbers are not the same. You could do the crisscross thing, but then you got to be careful. If you crisscross, what are you going to get? Ru2O4. Is that the lowest ratio? No, it's not. So you would need to reduce that. You're going to get Ru2O. Sorry. No. Ru02. I wonder if this is a compound. Are you okay? Ru 4+ and O2-. So if we do it this way, get rid of the bad joke. We've got -2 and we've got +4. So we need more of these. So if I draw another one in, now I've got -4 and I'm good. I've got 1 ruthenium and 2 oxygens. Any questions? Naming ionic compounds that have polyatomic ions. The pattern of naming is the same. It's just that polyatomic ions have special names, and you have to memorize them. They are named the way they are because a bunch of scientists got together and decided to call them that, and then everybody else just kind of has to go along with it. You've already memorized a bunch of these. So when we name something like NaO2, very important to remember, we're only going to do with ionic compounds that have 2 ions. There are some that have 3 or more ions. We're not going to learn how to name those in this class. So all of our ionic compounds, 2 ions, 1 positive, 1 negative. So when we look at NO2, what sometimes students do is they'll take it apart into sodium, nitrogen, and oxygen, and they'll tell me it's sodium nitrogen dioxide. Creative, communicative, descriptive, but not right. Okay? So sodium is a metal. That's the first ion. Everything else is treated as 1 ion. NO2, and the charge is -1. That has the name nitrite. So this is sodium nitrite, not sodium nitrogen dioxide. Okay. These are some common polyatomic ions. Many of these are on the memorization list. Things like hydroxide and carbonate and hydrogen carbonate and phosphate, and a whole bunch of these were on the list. Some of them were not, like hypochlorite, chlorite, and perchlorate were not on the list. That's because if you know what chlorate is, I'm going to show you how you can figure out what the other 3 are. Hydrogen sulfite, hydrogen sulfate, they are also called bisulfite and bisulfate. I try to avoid those names because I think they're a bit confusing. I think hydrogen sulfate is the proper name, and it's also more descriptive of what it is. Hydrogen sulfate ion is a sulfate ion with a hydrogen on it, and that affects the charge. And then there's dihydrogen phosphate, has 2 hydrogens. This is one of the few places where you're going to get a prefix, a numerical prefix in an ionic compound. It's when you have dihydrogen phosphate. So most of those ions are what are called oxyanions. They're anions that have oxygen in them. And so there is a pattern to how they're named. If there's 2 ions in the series, the one that has more oxygen atoms in it gets the ending -ate, and the one with fewer is -ite. So we've got nitrate and nitrite. The difference is the number of oxygens. Nitrate has 1 more oxygen than nitrite. Sulfate and sulfite, the sulfite is 1 less oxygen than the sulfate. The number of sulfur atoms doesn't change, the charge doesn't change, just the number of oxygens. Some elements form a series of 4 ions. And then we use prefixes hypo, that means less, and per, that means more. So chlorine, here's chlorate. That was on your list to memorize, ClO3 minus. Chlorite has 1 less, and hypochlorite has 1 less than the chlorite. Perchlorate has 1 more. Bromine and iodine follow the same pattern. So remember we talked about families in the periodic table, and I said the nonmetals are feminine. So chlorine, bromine, and iodine being 3 females in the same family, that makes them sisters, right? Sisters often have similar interests. They'll do similar things or look similar. So chlorate and bromate, same number of oxygens, same charges. What do you think the formula for iodate is? IO3 minus. That's iodate. You won't see these bromine names, bromine ions, their names and formulas on the list, and you won't see the series for iodine, but they exist and they're named exactly the same way. You just substitute in the different element. Okay. So what I want you to do is memorize the 8s. Those, you should have already done that. It's on the list. You memorize the 8s and then the pattern. Now, I've done this upside down of what's in the text because this makes a lot more sense to me. And since I made the slide, I get to do it upside down if I want to. So, chlorate, ClO3 minus, you just memorize that. Flat out, there's just no way around it, memorize that. Perchlorate, per, like hyper, means more. Hyperactive, more active, right? So perchlorate has one more oxygen. Chlorite is the light version. Bud Light has a third fewer calories than regular Budweiser, right? Chlorite has a third fewer oxygens than regular chlorate. One less. Hypochlorite is one less than that. Where does a hypodermic needle go? Under your skin. Below your skin, your dermis. Hypodermic means below the skin. So this is one less. Okay? So by memorizing chlorate and the pattern, you can actually do names and formulas for 12 polyatomic ions. That's pretty good, I think. Okay, name the compound SnClO3 your book doesn't specifically talk about these parentheses. The parentheses are there because what this is we've got one tin ion and we have chlorate ion, and there's two of them. And if I just put a 2 out here, that kind of looks like 1 chlorine and 32 oxygens, right? This is a package deal. Chlorate is 1 chlorine and 3 oxygen atoms. They're covalently bonded together. They're kind of like shopping at Costco, right? You go to Costco and you want to buy 1 bottle of ketchup. Well, you can't buy 1 bottle of ketchup because there's 2 of them shrink wrapped together, right? So I see the parentheses as being like shrink wrap. And on the outside, it's telling us how many of those do we have. So this is 1 tin ion and 2 chlorate ions. Now, the fact that there's 2 chlorate ions does not show up in the name. We're not going to say dichlorate or anything, but we're going to need to just be able to recognize what that means. So naming 2 ions, tin is the first one, and the second one is everything else. So don't tell me chlorine trioxide, right? That has its own name. So Sn is tin, I gave that away. Is tin in groups 1A, 2A, 3A zinc or silver? Nope. So what does that mean? It needs a Roman numeral. Put parentheses there to save a space for the Roman numeral. And I already gave this one away too. The name of that ion is chlorate. So this is tin something chlorate. So I've got tin and I've got 2 chlorate ions. What's the charge on a chlorate ion? -1. So there's 2 of those. That's a total of -2 charge. I must have a total of +2 charge for all the charges to add up to 0. So that means my tin has a +2 charge. That tells me the Roman numeral. So tin 2 chlorate. Any questions? Write the formula for cobalt 2 phosphate. What's the symbol for cobalt? CO. Make sure that you make your O's small, because capital C, capital O is carbon monoxide, which is significantly different from cobalt. What does the Roman numeral 2 tell me? That's a +2 charge. It gives me the charge. I don't have to figure anything out. It just says the charge is 2. It tells us that because there's no other way for us to know which cobalt ion is in this compound. What's the formula for phosphate ion? PO3 -1 is a great guess. PO4 3-. What? Okay, the 8 does not mean 3 oxygens and a -1 charge. That's a good guess because most of them, by numbers I guess, would be that way. But it's just whatever that one is. So phosphate is PO4 -3. Phosphite would be PO3 -3. There are reasons, but they're not worth going into. How do we put these 2 together? Where did I get the 4? I memorized it. Phosphate is PO4 3-. Yeah, so you just have to memorize it. There is a pattern based on the periodic table, and my husband explains it, and It just doesn't work with my brain. So if it works for you, do you know the pattern? He will explain it to you. Ask Luke. He'll explain it to you. Yeah, that guy. Okay. How do we put these together?
CO3, parentheses, PO4, and parentheses 2.
Yeah, we need to put parentheses because if we don't, we get that. 42? No, this is a package, and there's 2 of them. There's 3 cobalts. Crisscross works really well on this one. The 3 comes down, and the 2 goes down. Or you can draw pictures, or you can look for the least common multiple of 2 and 3, which is 6. Any questions? Hydrated ionic compounds. Some ionic compounds, when they form a solid from a solution, will incorporate some of the water molecules from the solution into their crystal structure. And so these are compounds, not just wet ionic compounds, because there's a definite proportion of water molecules to ionic formula units. So this example here we have cobalt 2 hexahydrate. If I take that and heat it gently, the color will change, and I'll end up with anhydrous cobalt 2 chloride. Hydrate. When you hydrate yourself, when you make sure you're hydrated, what are you doing? You're drinking water, making sure you have enough water. If you're dehydrated, that means you need more water, you don't have enough. An is a prefix that means without. So it's not just that you're lacking in water, it means that there's no water. Anhydrous means there's no water in it. Not all compounds do this. You don't need to know which ones do, but we just need to know how to name and write formulas for the ones that you get presented with. You may have heard of Epsom salts. It's good for soaking sore body parts in. That's magnesium sulfate heptahydrate. For every magnesium sulfate pairing, you have 7 water molecules in the crystal lattice. That changes the density, the molar mass, several different properties of the magnesium sulfate. So when we name these, we name the ionic compound, and then we use a numerical prefix to indicate how many water molecules are associated with it. So here are the prefixes. You should be familiar with most of these. You might not be familiar with hemi, but what's the hemisphere? Half of the Earth, right? There's the northern hemisphere and the southern hemisphere. Hemi means half. So when we name these, we name the ionic compound. So CaSO4 would be what? Calcium sulfate. Calcium does not need a Roman numeral because it's in group 2. SO4 is sulfate because SO4 is sulfate. And then the 1/2 is the prefix hemi, and the water is hydrate. Does it bother you that there's a half of a water molecule in there? Yeah. What's up with that? Actually, what this is there are 2 calcium sulfate units for every 1 water molecule. But that would get confusing, and so they decided to use a fractional prefix. So the anhydrous compound's name is always the same. We're not going to put 2's on it or anything, and we adjust the number of water molecules. So this is giving us the ratio. You can't have half of a water molecule. CaCl2.2H2O. What's the name? Calcium chloride dihydrate. So there's two water molecules. This dot, we haven't learned about calculating molar masses of compounds, but if we were doing that, that dot does not mean that you multiply. It just means that those 2 guys are together as a hydrate. And if you heat it, you can get the water to come off. This doesn't mean multiplication. Barium hydroxide octahydrate. Write the formula. What's the formula for barium ion? Ba 2+. Because barium is in group 2, it has a +2 charge. What's the formula for hydroxide? OH minus. Why? Why? How did you know that? You memorized it, yes. Okay, so how do we put these two together? Ba and then OH in parentheses with a 2 on the outside. We only use the parentheses when we have more than one. If we have sodium hydroxide where sodium is +1, we have NaOH. There's no confusion for sodium hydroxide without the parentheses, so we don't write them because we don't need to. So we do need the parentheses here, and then the octahydrate, we write a dot, 8 for octa, and the formula for water. Any questions?